Hey everyone, welcome to this new playlist where we are diving into the world of sorting algorithms, one of the most fundamental concepts in programming and data structure. In this series, we'll not just code these algorithms in C, C++, but also analyze them based on multiple criteria like time complexity, space uses, stability, and how they behave under different input conditions. So, throughout this playlist, we will explore a wide range of sorting techniques. On basic and comparison based sorts, we'll see bubble sort, insertion sort, selection sort, heap sort, merge sort, quick sort, tree sort, and cell sort. And we'll also cover the efficient index based sorts like count sort, bucket sort, and radius sort that offer a real time complexity while leveraging extra memory. So each algorithm will be explained clearly with dry runs, code walkthroughs, and performance analysis. So you get a solid grip on not just how they work, but why and when to use them. So in this first video, we'll start with a criteria-based analysis to help you understand how to compare and evaluate different sorting techniques, even before you write a single line of code. So let's get started. Okay, so we'll start with the criteria for analysis of sorting algorithms. So there are a few criteria which we have to take in consideration whenever we are analyzing any sorting algorithm. Okay, so first one is the number of comparisons. So basically, algorithms are mostly of two types. In first one, there is a comparison based on the elements. Okay, so the comparison is done between two elements and then the resultant is okay swapped. Then there is index based. Okay, so based on number of comparisons, the actual analysis is done, and the total time taken by the sorting technique also depends on the number of comparison only. Okay, so this is the very important part, that how many number of comparison are actually done in the algorithm to sort that particular data set. So okay, then there is number of swaps. Now swaps we will consider the whenever the comparison is done, and if one element is less, means is less than the other element or greater than the other element, so based on the algorithm we will perform the swap, or we will not perform the swap also. Okay, so there will be both the conditions, but we will consider that the maximum numbers of swaps that can be performed, okay, when the sorting algorithm is totally in that case. Okay, so yeah, so we will consider the maximum number of swaps whenever we will perform the analysis on any sorting algorithms. So number of swaps is the second thing which is have to be taken in consideration, and most of the time the number of comparison and number of swaps remain same only. Then there is adaptive. Okay, so as you can see, I've written here adjust to already sorted data for minimal time. Okay, what does it means? It means that if any algorithm is taking less time or minimum time over already sorted list or any data set, so is will be, so that particular algorithm will be called as adaptive. Okay, now why it will be adaptive? Suppose for, let's consider bubble sort. Okay, so the time complexity taken by the bubble sort is degree, or you can say theta, but we will consider degree only. So degree of n square. Okay, now what is this n square? It is the maximum number of time which can be taken by this algorithm. Okay, actually the maximum number will be n cube. So average, let's consider average. So average time taken by the bubble sort algorithm is n square, degree of n square. Okay, now what happens if the list or the data set is already sorted and then we are applying bubble sort? Then what time it will take? Okay, so in that case the bubble sort will take a minimum of time, so that's why it will be called as adaptive. So we will see, whenever we'll see all the sorting algorithms, so we will discuss there and we'll see on performing a already sorted data set that it is adaptive in nature or not. So this is adaptive. Okay, then there is stable. Okay, now it maintains relative order of equal elements. Okay, now what do you mean by this? See, if the algorithm is preserving the order of duplicate elements in the sorted list, then the algorithm will be called as stable. Okay, Now for this I'll need to switch to my VS Code screen. So before explaining stable, I'll explain extra memory. Okay. Now extra memory, there are some algorithms which take extra space. Okay. Just like bin sort or radix sort, these are some algorithms which are more efficient in comparison to time complexity, but they consumes more space. So space complexity is more, but the time complexity is less, but they are more efficient in comparison with other algorithms, okay, on the basis of time. So yeah, so they will- so we will see that which algorithms take extra memory and how they take extra memory. That we'll see when we'll discuss all the sorting techniques. Okay. Now, here I have created a table, as you can see, of all the algorithms which we are going to discuss, okay, in this particular playlist. And with respect to their time complexity, I've written the time complexity of them also, okay. And the category, you can see the category also. So as you can see, bubble sort. Bubble sort has a time complexity of degree of n square, and the category is it is comparison based, okay. So same goes to the insertion sort and selection sort also. They follow the same time complexity, degree of n square, and they are comparison based. Now, heap sort. Heap sort has less time complexity as comparison to bubble insertion and selection sort, degree of n log n, and the category is also same, comparison based. So similar merge sort, quick sort, and tree sort, they have the same time complexity as degree of n log n, okay, and they follow the comparison based. Now, the cell sort has different time complexity. As you can see, the time complexity of cell sort is degree of n to the power 3 by 2, it means 1.5. So basically, you can consider it, you can consider cell sort as better than bubble insertion selection, but uh, not better than heap merge quick and tree sort. Okay, so yeah, and it is also a comparison based sorting algorithm. Then there is count sort, bucket sort, and radix sort. So they are basically the index based sorting algorithms, and because of their index based, they consume an extra space, okay. And you can see the time complexity is degree of n, so they are more better than the other in consideration of time complexity. They are more better than the other eight, these eight which are comparison based. But the one problem is that in space they consumes more space, okay. Yeah, now let me explain you about stable, okay. So let's switch to my main coding screen. Okay, now we'll discuss about stable. So for explaining stable, I'll take a small example, okay, and that example will be, I'll take name. Suppose I have A, B, C, D, and E, okay. Okay, now I'll do what? Suppose all these A, B, and C are the names of players, and we are going to give them scores. So suppose 1, 2, 3, 4, and 3. Okay. Now take it as a data set. Okay. So these are the values, and the names assigned with these values are A, B, C, D, and E. So they are already sorted on based of names. Okay, on the basis of name, they are already sorted. As you can see, A, B, C, D, E. Okay, but on the basis of score, suppose, wait, let me make it 5, make it 10, 3, 4, 3. Okay, yeah, or let me take a single digit value, 9, 3, 4, 3. Okay, now on the basis of scores, they are not sorted. Okay, as clearly we can see. Now if we have to sort on the basis of scores, so then how it will look like? Okay, suppose sorted scores, if we have to sort it on the basis of scores, okay, so then it will look like somehow like this: 3, 3, 4, 5, and 9. Okay, now which 3 is at the first place and which 3 is at the second place? So let's write the name also. So sorted name, and okay, so the first 3 is the C, second one is this D, and then 4. Okay, wait. no, not D, E. Then D, 5 was A, and 9 was B. So now you can see that in the previous one, when it was sorted on the basis of name, so first there was first of all duplicate values, and duplicate values were on C and E. So first there was C. So that value, that same thing should be preserved, okay, which was in the previous sorted name. First there was C and then there was E. So that should be preserved. If it is getting preserved in the next time we are doing the sorting thing, if the same criteria is followed and if it is preserved, suppose first C is there and then E is there, okay, so same thing is preserved, so then we will call it as stable, that this particular algorithm is stable. Okay, so yeah, that is stable. I hope you have understood. Again, I'll repeat the definition of stable. If the algorithm is preserving the order of duplicate elements in the sorted list, then the algorithm is called as stable. Okay, so yeah, that is stable. I hope you have understood all the criterias for doing the analysis on the sorting algorithms. So now from the next video onwards, we'll start with our sorting algorithms, and on that sorting algorithms only itself, we are going to discuss about all these analysis. We'll perform all these analysis and we'll see that how that particular algorithm is efficient or it is not efficient, why this algorithm is there, and when to use that particular algorithm. So I hope you like this video. You have understood all the criteria for analysis. Thanks for watching the video. Stay tuned up. We'll see you in the next video.